All right, let's jump right in. We usually think we know what a shape is, right? It's about its size, its angles, all its specific curves. But what if I told you there's a much deeper way to look at shapes, a kind of rubber sheet geometry, where all the normal rules just go out the window? That's topology, and trust me, it's a wonderfully weird world. So to get us started, let's ask a classic question, one that really gets to the heart of what this is all about. Take a look at these two things, a coffee cup and a donut. They seem totally different. One holds your coffee, and for some of us, the other one is the coffee. But to a topologist, they're hiding a pretty amazing secret. And that secret is they are the same, exactly the same. Now, I know that sounds completely bonkers, but stick with me, because it's the key to understanding how topology sees the world. It's not about what things look like, it's about what they fundamentally are. So, how on earth is this possible? Well, the magic word is homeomorphism. Just imagine your coffee cup is made of some infinitely stretchy clay. You could slowly smoosh the cup part down, kind of thicken up the handle, and gently morph the whole thing into the shape of a donut. And the key is you did it all without ripping any new holes or gluing any bits together, because you can transform one into the other. In topology, they're considered the same thing. This idea of just completely ignoring measurement, it's pretty radical. It means topology is basically the study of shapes with all the geometry stripped away. We're throwing out our rulers, our protractors. The very idea of distance and length is gone. So, what in the world is left? Well, think about it. If you can't use distance to say that 2 points are close, how do you even begin to define a space? This was the big fundamental problem that topology had to solve. And the solution is just brilliantly simple. Instead of measuring, we just declare that certain groups of points are neighborhoods. A point is considered near another one if they share a neighborhood. That's it. This abstract idea is called a topological space, and it's the stage where all of this plays out. You know, the power of this whole thing is just how simple it is. As long as these neighborhoods follow a few basic rules, we have a perfectly consistent system. And from this one simple idea, just defining who is near whom, the entire massive field of topology is born. Okay, so we've established that a coffee cup can be turned into a donut. But we all have this gut feeling that, say, a basketball can't be turned into a donut unless you tear a big hole in it. How do we actually prove that? For that, we're going to need some tools. This is really the crucial question. We can't just go on a hunch. We need a rock-solid mathematical way to prove that these two shapes are fundamentally different. A way to show that no matter how much you stretch or bend a sphere, it will never, ever become a donut. The answer is to find what's called a topological invariant. You can think of it like a shape's fingerprints or its DNA. It's some core property that doesn't change no matter how much you deform the object. And if two shapes have a different invariance, well, then they simply cannot be the same thing. It's mathematical proof. And one of the most powerful and thankfully intuitive invariants is something we can all understand: the number of holes. A sphere has 0 holes, a donut has 1. And you can't just create or destroy a hole by stretching something. But how do we actually get a number for that? We do it with this incredibly clever calculation called the Euler characteristic. The way it works is you imagine drawing a network on the surface of your shape. Then you just follow this simple recipe. Count the points, or vertices, subtract the number of lines, or edges, and add the number of regions, or faces. Amazingly, the number you get is always the same for that shape, no matter how you draw the network. So, let's run the numbers. For any sphere, no matter how you draw your network on it, the Euler characteristic always comes out to 2. That corresponds to its 0 holes. And for a torus, a donut, that number always comes out to 0, corresponding to its 1 hole. And there it is. That's the proof in black and white. Since 2 does not equal 0, a sphere and a torus have different topological DNA. We have now mathematically proven, beyond any doubt, that they are different objects. Case closed. Now, this might all seem like a really abstract, cool math game. But here's where it gets truly wild. These deep, hidden properties of shape, they have profound, unbreakable consequences for the real physical world. And there's one famous example that shows this perfectly. No, that's not a joke. It's the real, informal name for a huge discovery in topology, the hairy ball theorem. So picture a tennis ball that's completely covered in hair.
The theorem says that no matter how you try to comb that hair down flat, you will always end up with at least one cowlick, a spot where the hair just has to stick straight up.
So, what does that mean? Well, think about wind patterns swirling around the Earth. The hairy ball theorem proves that at any given moment, there has to be at least one point on the planet with zero wind speed. An eye of a storm is mathematically guaranteed to exist somewhere, always. This isn't a rule of weather, it's a rule of shape. So why? Why is that cowlick guaranteed to exist? Well, it all comes right back to our invariant number. A really deep theorem proves that any shape whose Euler characteristic is not zero simply can't have a perfectly smooth, continuous flow across its entire surface. And we already know the sphere's number is
2. That little number is a fundamental roadblock. It's the sphere's unchangeable signature, and it forces a disruption, a cowlick, in any continuous system that lives on its surface.
But what about the doughnut? Remember, its Euler characteristic is zero. And that tiny difference changes everything. Because its number is zero, the theorem doesn't apply. That means you can comb a hairy donut perfectly flat, with no cowlicks anywhere. Zero, it isn't just a number here. It's like a permission slip. It allows for a perfectly smooth, harmonious flow, something the sphere, because of its fundamental shape, can simply never have. So the big takeaway here is this. Topology isn't just some abstract game. It reveals this hidden layer of reality. The deep, essential structure of a space actually imposes absolute, unbreakable rules on everything that happens on it, from weather patterns to the laws of physics. And that leaves us with a pretty incredible final thought. We just saw how something as simple as the number of holes in an object can literally determine whether a storm must exist. It really makes you wonder, what other profound truths about our universe aren't written in the laws of physics, but are hiding in the simple, secret rules of shape?